for today's lesson, we talk about numbers of standard deviation that aren't whole numbers. So we start today's lesson with a vocabulary term. And your vocabulary term for today's lesson is z-scores. When you calculate a z-score, what you are actually calculating is a score for a data value. You're giving it a score. That score is associated with the number of standard deviations either above or below the mean. So when you calculate z, yesterday you were getting either 1, 2, or 3. But when you calculate z today, you can get like 0.68. You can get decimal varieties for your number of standard deviations. So that's what we're going to work on today. To do this z-score, we do have a formula, and you calculate it like this. Remember, you're always trying to establish some sort of relationship between your data value and the mean. So the top part of the formula is just x minus x bar. To get the actual z-score, you then divide by your standard deviation. So let's make it official and assign some values or quantities to each of the symbols in this problem, or in this formula. Z is a number of standard deviations above or below the mean. If your z-score works out to be a positive number, in other words, your data value was larger than the mean, you're going to be above average, your z-score will be positive. If you think about it, if your data value is smaller than the mean, in other words, your data value is below average, your z-score is going to reflect that. Your z-score is going to be negative. X, by the way, just to reiterate, is the data value that you're working with. Little new verb for you. If you want to normalize a piece of data, that's what you're doing. You're trying to figure out how it fits into the bell curve when you do this. X bar, you know what that is, right? It's your mean, very good. And sigma x, you know what that is, right? Standard deviation, very good. Not your number of standard deviations, that's the z-score. Sigma is your, if I could spell, your standard deviation. Okay. So to kick off this particular lesson, we really only have 2 examples to get through today. Then I'll come around and check off your bookwork from last night. Yeah, we have an arithmetic skills test to think about. And a school district gives a basic arithmetic skills test to all of its students. Data from the tests are shown in the table below. So you see they broke their data down into age groups, found the mean for each age group, and found the standard deviation for each age group. Part A. Gina is an 11-year-old who had 113 correct answers. Michelle, she's 18. She scored 157 answers correct. I need to answer the first bullet for me. Is it fair to compare their scores directly? In other words, is Michelle automatically, just mathematically, more talented because she got 157, but Gina got 113? You're all shaking your heads. For the folks at home, what do you think? No, yeah, it's not fair. All right, who can tell me why? What do you think, Grace? Yeah, it's not fair. It's mean. Michelle, being 18 years old, has more exposure to arithmetic because she's been through some more math classes. However, Gina, well, she's only 11. What is that, like 6th grade? Yeah. Okay, so now you're taking us into the next bullet. Evan is thinking, there should be a way to compare these ladies. Yeah, so that takes us into the next response. So hopefully you jotted down your response to the first bullet. And Evan's like, man, there should be a way to compare these people. And there is. That's what we're doing. We can use z-scores to do such a thing. What we're going to go ahead and do is calculate each lady's z-score using our z-score formula. So in the next bullet, we are going to calculate a z-score for Little Miss Gina and then Big Bad Michelle. Michelle, it's my mom's name. I'm telling her, Evan. I'm just kidding. Okay, so Gina's z-score, you have to take her data value and again compare it to the mean. Find out how it's different from the mean. Essentially subtract the mean from her data value. So she scored 113 correct, minus the mean for her age group, which was 102.4, and divide by her age group's standard deviation, which was 16.3. Michelle scored 157 correct answers. And now I'm going to go ahead and compare her value to her age group's mean. So the mean for her age group was 146. Ooh, I hear you clicking buttons. Should probably talk about that for a second. Standard deviation, 18.1. If you have an old school calculator, be careful. When you go to type this in, you do have to quantify or put parentheses around your numerators, or else it's going to try to take your 102.4, divide it by your 16.3 first, and then subtract it from 113. You will get the wrong answer that way. So please make sure you actually find the difference in your numerator first, and then divide by 16.3. So you're calculating your z-scores right now for each lady. And then we're going to talk about those, of course. Hundredths. All day today, 2 decimal places. All right, so we have 2 z-scores, plot 2 sticks here. Hey, Lauren, what'd you get for Gina's z-score there? These are not percents. Absolutely not percents. Z-score is a number of standard deviations above or below the mean. We don't get the percents till later. Remember, they lead to each other, Lauren, but they are not the same thing. If they say a number of standard deviations, you can look up the percent. If they give you a percent, you can look up the z-score and find the number of standard deviations, but they are not the same number. So you can't say it's a percent. This will be it's like saying, Lauren, it would be like saying, last night on the homework you got 2 for a number of standard deviations. That's like saying it's 200% chance of happening. Can't say that, you know what I mean? So these are not percents. I'm actually glad you said that because that'll clarify for some people. And again, Lauren, what was your decimal? 0.65. And then Alex, what did you get for Michelle? 0.61. Okay, now let's discuss. What we have established is a score now relative to each girl's age group. So now we can make a conclusion about who, as Evan was saying, hey, within their age groups, couldn't we make a comparison? Now we can make that comparison that maybe Evan wanted to make a little bit earlier. So which girl is doing better when you compare her to her age group? What do you think? Gina, yeah, her z-score is higher, yeah. So Gina is doing better when we look at just the z-scores. There are questions about that? To be clear, z-score is a number of standard deviations, and notice both of these numbers were positive. So if we go back to our definition from before, when you get a positive z-score, our data values were indeed above average. Both girls scored above average, so they did well, relatively speaking. But who did better within their age group? Well, because the z-score was more positive, bigger than Michelle's, Gina actually did a little bit better. Okay, now what we're going to do is talk percents. So how does this connect to like the probability that, Gina did better than her peers? What percent chances does a student have to score better than Gina? We can answer those questions if we understand the next example. So what we have here are heights, and I did tell you yesterday, when we were talking about this stuff, that heights of adult women and men are normally distributed. They fit a bell curve. Here's that. In our height problem, keep in mind we are going to use a z-score in this problem and the standard normal table, which is the piece of paper you grabbed when you walked in. You got a little z-score chart for me. You will be allowed to use it on your test. You can't memorize those decimals, that's for sure. So you'll be allowed to use the z-score chart on your test. You should only write your name on the z-score chart and nothing else. So you cannot write the z-score formula on there. You can write your name and nothing else. I will walk around and check to make sure you're not like trying to use this as a cheat sheet or whatever. In addition, you want to put your name on this paper because if you lose it, I only have so many extra copies. You put yourself in jeopardy of not being able to use one. So please make sure you don't lose this paper. So we have a survey of a group of women found that the height of the women is normally distributed with a mean average height of 64.5 inches. So in this data, the average is taller than me because I'm 64 inches even. So a height of 64.5 inches and a standard deviation of 2.5 inches. In part A, we're asked to find the probability or the percent chance that a woman is at most 58 inches tall. Well, if they're asking you to find a percent, just like in yesterday's lesson, you have to find a number of standard deviations. And for today, that's a z-score. So I need to find a z-score for the woman who is 58 inches tall. So I'll go ahead and run the calculation on that. 58 inches is below average, which means our z-score is going to be negative. Watch what happens. If I compare 58 to my mean, 58 minus my mean is 64.5. We're going to get a negative data value in our numerator, and we're going to divide that by 2.5, by your number of standard deviations. So you throw that in. When I number crunched that this morning, I got negative 2.6. That is a z-score. It is not the probability of the event. To find the probability of the event being at most 58 inches tall, we have to go to table A, our z-score chart. Looks like that. Step 1, make sure you're looking at the right side. We did calculate a negative z-score. Notice one side is for your positive z-scores. The other side of your standard normal table is for negative z-scores. Notice the percent of the graph that's shaded at the top. That's kind of also your visual cue to let you know you're looking at the right side. This side, with negative z-scores, we have data that's below average shaded. Whereas if you get a positive z-score, you're shading above the average. So that's kind of another visual reference for you. If we're looking up a z-score of negative 2.6, you want to keep in mind that your standard normal table will actually calculate percent probability based on a z-score that's calculated out to the nearest hundredth place. So we know that negative 2.6 is the same thing as negative 2.60, right? So that's the z-score I need to look for on table A. So here we go. Up here I start at like negative 3.5, which, 0% chance means you're talking like all the way down here on your standard normal table there, or your bell curve. So we're at negative 3.5, almost no percent chance of that happening, and then it works its way up a little bit. Negative 2.6 right there. And because I need negative 2.60, I go over to the 0.00 column. If I needed negative 2.61 as my z-score, I would go out another column. If I needed negative 2.62, I would go out another column. If I needed negative 2.68, I'd go all the way over here. But I just need negative 2.60. The percent chance that a woman is at most negative 2.6 standard deviations below the mean is 0.0047. So this gives me 0.0047 when I look up that z-score. That means that we have a 0.47% chance of running into a woman in this survey that is at most 58 inches tall. Keep in mind, 58 was pretty well below the average. Not very many ladies are going to be that far below the average. 0.5%. Questions about that? All right, let's do it again. This time around, we're going to do the same thing, but I did change one number. We're asked to find the probability that a woman is at most 70 inches tall, well above the average. Our z-score this time around, going to be positive because she's above average. So I'll go ahead, step one, I got to calculate the z-score. When they ask you to find the probability, they're asking you for a percent chance. And to find a percent, you have to find a z-score. If they give you a percent, if they give you the z-score, you can look up the percent. So, take my data value, subtract my mean, divide by my standard deviation. And when I ran the numbers on this one this morning, I got 2.2. So now, I got to go to my standard normal table, and I have to look up a positive z-score of 2.2. Keep in mind, the negative m was talking about below average heights, and I had to go to a positive z-score, so I'm going to flip the paper over. And now I need to look up a z-score of 2.2, which does equate to 2.20 to the hundredths place. So 2.2 is here. 2.20, I have to go over just one column. So I got 0.9861 is the value I'm looking for. Which is 98.61%. 98.61% is the probability that a woman is at most 70 inches tall. Now, because what I'm running into today is problems with at least and at most, we're going to do a part C. Part C. You can add it in there. I want you to find the probability that a woman is at least 70 inches tall. You're going to do that one as a little bit of independent practice. Ready? 1.39%. Yay, good job. Yeah, if you put the probability of the events together, ultimately they are in reality complementary. You didn't have to recalculate a z-score. If 98.61% of women are at most 70 inches tall, the leftovers are at least 70 inches tall. So you just do 100% minus your 98.61%, 1.39% is what you get. Okay, other questions about that? No? Okay, so you get to turn your attention to your homework assignment for tonight. Somebody asked me in my period 3, what is the stuff on the back? That would be the answers. That stuff would be the answers. Now, use them carefully. Use them for good, not for evil.